Okay, so this is pretty much the last lecture. It certainly is the last lecture for any new content. I might have a partial lecture where we follow up with some additional applications other than the one or two that I'll do here today. But otherwise, the central limit theorem, this is the capstone. This is sort of where everything has been leading to. So let me just lay out essentially what the central limit theorem says now, and then we'll go ahead and state it more specifically and prove it. So what the central limit theorem says is, let's just suppose that I have this set of random variables, x of i's, that are independent and identically distributed. So these x of i's are all independent of each other, right? Or they're independent and they have the same distribution. And let's say we don't know what that distribution is. It actually doesn't matter for the most part, right? But let's just say we know that the expected value of the x of i's is equal to mu, and the variance of those x of i's is equal to sigma squared. Okay. So now we want to make a statement about S sub n, which is the sum of n of those random variables. Okay. So I want to sum n independent and identically distributed random variables. Okay. And what the central limit theorem tells me is that S sub n is approximately normally distributed with mean n times mu and variance n times sigma squared, at least as n approaches infinity. Okay. Actually, let's state it this way, that if I take this random variable, this sum of random variables, and I subtract off its mean and mu, and I divide by its standard deviation, square root of n times sigma, then what I have is a standardized random variable z sub n, and the claim is that that will approach a standard normal random variable as n approaches infinity. And the beautiful thing about this is we really are not assuming anything about our random variable other than it has a finite expected value and a finite variance attached to it. So if I sum up enough random variables, then my sequence of new random variables, which are the sum of the old random variables, when I normalize them, will become, in the limit, the standard normal random variable every time. Great result, right? Because we've had this normal random variable and it's not been clear where it fits into everything, and it turns out it fits into everything, at least if we start summing independent copies of any of the other random variables that we've been dealing with. Okay. All right, let's take care of this. So, central limit theorem, let's give the statement. Let's let x1, x2, be a sequence of independent and identically distributed random variables with mean 0 and variance sigma squared. Now, let me just make it clear here. So when I state this, I'm going to look at the specific case where the mean is equal to 0. But what is that? Well, that's any of these random variables if I just subtract off the mean. Okay. So it's just going to make our calculations nicer, not having to deal with that extra term. But of course, I can always put it back to whatever mean I want it to by adding the mean back on, and of course, it doesn't change the variance. So the mean and the variance of sigma squared, and right, they have a common CDF, which we'll just call capital F, and a common moment generating function, which we'll call m sub t, okay, which is defined on an open interval containing zero. Okay. All right. So this assumption we've been making about our moment generating functions, that if I'm going to have this one-to-one correspondence between moment generating functions and cumulative distribution functions, my random variables, I ask that they're defined on an open interval containing zero. We'll actually see why in a moment, because we're going to use a Taylor expansion. So let S sub n equal to the sum I equals 1 to n of x sub i's. Then, so here's the statement. The limit as n approaches infinity of p of s sub n minus sigma square root of n is less than or equal to x is equal to p of x, or negative infinity less than or equal to x less than or equal to p. Let me double check something very quickly. Yes. Okay. So essentially what this is saying is that if I normalize my random variable, so I picked one whose mean was equal to 0, but of course if the mean wasn't equal to 0, I could subtract off the mean and then it would be equal to 0, right? So if I normalize these random variables s sub n by subtracting the mean, 0 times n, and divide by their standard deviation, which is going to be sigma times the square root of n, and I look at the problem. So this is the cumulative distribution function for the normalized version of my S sub n's. Okay. Then it says that these things are the cumulative in the limit as n goes to infinity equal to the normalized, or not the normalized, the standard normal, the cumulative distribution function for the standard normal random variable. Okay. So that's our statement right there. So how are we going to do this? Remember, we have these results from last time that say things like, well, if I can just show that the moment generating functions converge to the moment, right? The moment generating functions of the things over here converge to the moment generating function of this guy over there, which we know what the moment generating function of that guy is, then we can go ahead and show that the cumulative distribution functions converge, which means that the random variables converge. Okay? So here's what we're going to do. Here's our proof. We'll prove this and then we'll see some examples. Prove let z sub n equal s sub n divided by sigma square root of n. Okay. And we will show, here's the goal, show that the moment generating functions for z sub n converge to the moment generating function for z. Z being the standard normal random variable. Okay. All right, so we're going to have to pull together everything we know about moment generating functions to make this happen. Okay. So let's just see if we remember what we can say. So we know the moment generating function for these guys, we're just calling m sub t. So the moment generating function for s sub n will equal to the moment generating function for the sum of a bunch of x sub i's, a bunch of independent x sub i's. And remember, if I'm summing up independent x sub i's, then I end up with the moment generating function of the product of all of those x sub i's. Okay. So that's going to be the moment generating function for x of t raised to the nth power. Remember, this is the statement that if I add, it's a continuation of the statement that if I add two independent random variables, the moment generating function of x plus y, if x and y are independent, will be the product of the two moment generating functions. Will be the product of the two moment generating functions. Okay. So now I'm going to add n independent random variables, and it'll be the product of those n moment generating functions, but they all have the same moment generating function. So let me just get rid of that x there because I'm just calling it m sub t, right? The moment generating function for the x, which is all in common. Okay? All right, so we have that result right there. Let's get rid of this and clean this up. We'll want that space in a little bit. And then the moment generating function for z sub n. So what do we have here? My z sub n is just a linear translation, essentially, or a linear function of my s sub n's. And remember, we have a way of taking, I'm not going to write this one down again because I've written it down in the last two lectures, the moment generating function of an a plus b t, right, or say a plus x t, a plus bx, and write down the moment generating function of that in terms of x. Okay. Now I have no a term, I have no constant term here, but I'm scaling s of n by this sigma squared of n in the denominator, and so it becomes moment generating function for my s of n with t over sigma square root of n, which is then equal to the moment generating function for, let's see, t over sigma square root of n, all raised to the power of n, where this is the moment generating function for each of those individuals. Right? This is the moment generating function for the sum, which up here is equal to the product of those moment generating functions. Okay? So here's what we have. Right? We have this moment generating function for z sub n is equal to the product of these moment generating functions, the product of n of them, with this t over sigma square root of n plugged into it. And now we want to make a statement about what happens to this thing as n goes off to infinity. Now there's a couple of ways to go about improvement. So essentially the statement here is, and we'll remind ourselves, because we know what the moment generating function for a standard normal random variable is, we just used it last time when we dealt with that Poisson random variable, it is e to the t squared over 2. So essentially our goal here is to show that it doesn't matter what moment generating function I'm dealing with. That if I perform this limit as n goes to infinity, it will always end up looking like e to the t squared over 2. Now that seems like a tall order. Seems like an incredibly tall order. That doesn't matter which function I start with, that if I take this limit right here, I'll always end up with an e to the t squared over 2. All right, well, let's just see how it works. Okay. So here's how I'm going to do this. I'm going to take my moment generating function m. I'll just put an s in it for a minute so I can substitute in my t over sigma squared of n later on. And I'm going to write the Taylor expansion for that moment generating function. Okay. That is valid because my moment generating function is defined on an open interval containing 0. So I could find the Taylor series of that about the point 0. So it will look like m of 0 plus, let's see, how do I want to write this? M prime of 0 times s plus m double prime of 0 over 2 of s squared plus m, let's write a third one, of 0 over 3 factorial, let's see, s cubed, plus some other things that all depend on s to the fourth. Right? I mean, we have these other terms here with increasing s values. Okay. So that's my moment generating function for my original random variable x. If I think about it in terms of the Taylor series expansion. Now, there's a couple of things worth noting in all of this. Right? For instance, moment generating functions, when I plug 0 into it, are always equal to 1. because I end up with the expected value of e to the 0x, right? I get the expected value of 1, which is always equal to 1. And the moment generating function, if I take the derivative of it and plug in 0, that's the expected value of x. That's my mu, which is equal to 0 in this case. And the second derivative of the moment generating function is my variance of x, which is equal to sigma squared in this particular case. And the third, I'm not sure what it is. Not sure what it is, right? Doesn't really matter for this purpose. So, if I'm looking at this moment generating, this Taylor expansion of the moment generating function, it will be 1 plus 0, right, plus sigma squared over 2 s squared plus, and then I'll just write it out here, I have this next term over s to the 4th, plus some other things that, oops, that's a cube, that depend on s to the 4th. Some other things that depend on s to the 4th. All right, so that's what we have, at least if we start writing out our Taylor series expansion. And what else do we need to know about this? Okay. As, get rid of this thing here. As n goes off to infinity, t over sigma square root of n goes to 0. So now if I look at the moment generating function of t over sigma square root of n, it will equal 1 plus, let's see, if I plug sigma squared over 2, and then I would have something like a t over sigma square root of n squared. Plus, right, the third derivative, whatever that is, over 3 factorial s cubed, but what's my s? Looks like a t plus sigma square root of n cubed plus these other things that are going to depend on t over sigma square root of n to the 4th power. And above, right? 4th, 5th, 6th, 7th, 8th. Okay. All right, so that's what we have there. Okay. So we have these other things, and when I go ahead and look at now the moment generating function for z sub n, it will be these things raised to the nth power. Okay. So let me just jump ahead there and just say, when I have this, it'll just be this thing raised to the nth power, which will be this thing raised to the nth power, equals that right there. Okay. All right. So what I really need to do now is figure out what this limit is as n goes to infinity. Okay. And my claim is, and I'll justify most of it, I'll leave one statement for you to finish justifying, but my claim is that this limit as n goes to infinity of m sub c sub n of t, right, this limit right here will equal e to the t squared over 2. Yep, that's my claim. Well, how is that the case? Or how could I end up seeing something like that? Okay. So let me just go ahead and write this, make sure I have plenty of room here. Figure out how I want to rewrite this term right here. I'm going to write it as a 1, that 1, plus, and let's just see how this all works out. I have this 1 plus, and then I have a sigma squared over 2, and notice I have a sigma squared right here when I square it, and I'll have a t squared. So I'll have a, let's see, I can write that as a 1 over 2 sigma squared, or t squared, t squared over 2, my sigma squareds will cancel out, and then I'll have this whole thing, I'll have a 1 over square root of n squared, right, which will be a 1 over n. Okay? And then I'll have this next term, which will be triple prime of 0 over 3 factorial, and I'll have a t cubed over sigma cubed n to the 3 halves, right? Plus, and in particular, I really want to know what's happening as n goes off to infinity. I have these other things here that depend on 1 over n squared and larger, right? And in particular, as n goes off to infinity, this thing is going to go off to 0. And of course, as n goes off to infinity, this thing is going to go off to 0 also. I'm going to jump down here because I want to write this out one more time. I'll actually write this as 1 plus 1 over n. I'm going to factor a 1 over n out of this entire thing here. And what do I get? I get a t squared over 2 plus, let's be a little more careful with this. I'm going to factor a 1 over n out of the whole thing, and what's left is a t squared over 2 plus this other thing, m triple prime of 0 over 3 factorial with, and again, when I factor, I'm going to factor a 1 over n out of this, I'm going to factor a 1 over n out of this, and I still get a square root of n in the denominator. Okay. And then these other things, when I factor out a 1 over n out of it, I'm still going to end up with other things that depend on 1 over n. And I'm going to raise that to the power of n. And now the question is, big parentheses here, big parentheses here, right? So I have this thing that looks like, switch over to white for a second, 1 plus a to the n over n raised to the nth power. And I would like to make a statement about what happens to that as n goes off to infinity. But I have an additional statement that these a sub n's are actually getting closer to some number, right? Because as n goes off to infinity, this is an x squared over 2 plus this thing will be getting closer to 0 because there's something in the denominator going off to infinity. And of course, all these things are going to go to 0 because there are things in the denominator that are going off to infinity. And so, so I have this thing is getting closer and closer and closer to t squared over 2. And I'd like to make a claim that if I have something of that type, 1 plus a to the n over a raised to the power of n, and I take the limit as n goes to infinity, if those a sub n's are all getting close to a particular number like that, then the limit will be e to the a. And if that's true, then it means this limit is going to be e to the t squared over 2, right? Because that would be my a for this particular case. Okay. Well, I don't want to prove this whole thing. I can just go back to, we can go back to Calc 1 and I can remind you of something, that if I do have a limit that looks like 1 over a to the n, right? 1 plus a over n to the power of n, and I want to take the limit as n approaches infinity, that this limit is e to the a. And how do we handle that? So let's see, how do we handle that? Then we take the limit as n approaches infinity. I would hit this thing with a natural log. I'll hit it with an e to the natural log. And if I hit it with the natural log, I'll get the n out in front, natural log or the log of 1 plus a to the n. Okay. And then I have something as n goes to infinity. This is going to infinity, and the natural log of 1 plus 0, natural log 1, is going to 0, so I have an infinity to 0. I have this indeterminate form just like I had back here with the 1 to the infinity power. And so I could move this n to the denominator here, and I could hit this limit with the L'Hopital's rule, right? So this limit should equal e to the limit, and as n approaches infinity of the natural log of 1 plus a over n to the, oops, I'm sorry, n to the negative 1. Okay. So I just need to calculate this limit. I'll use L'Hopital's rule. Let's see how much room I have. Plenty of room over here. L'Hopital's rule says, oh, that should be e limit as n goes to infinity. I'll take the derivative of the numerator, which will be 1 over 1 plus a over n, and then the derivative with respect of the inside function with respect to n would involve an a n to the negative 1. The derivative would be a negative a n to the negative 2. Okay. And the denominator, when I take the limit, will be a negative n to the negative 2. So I guess I'm just going to multiply the numerator and the denominator by negative n to the negative 2, negative n squared. That gives me a 1 in the denominator. Those two things cancel out, give me that. And now the limit as n approaches infinity, I now have e to the limit as n approaches infinity of a over 1 plus a over n. As n approaches infinity, that goes to 0. That's an a over 1, which is a, which is an e to the a. Right. Which is what we had said, right? So if this is a fixed value, 1 plus a over n to the power of n, then the limit is e to the a. You should remember that from Calc 1. Okay. Would have come up, probably came up in Calc 2 again with sequences and series. It's not the last time something like that will come up. And so what's new here, and I don't want to go through all of this because again, we're not in the Calc 1, we're not in the Calc 2 class, but if I have in the numerator not a fixed number, but I have a sequence of numbers that are all converging to that particular value, that are converging to that particular value of a, then the limit is still the same thing, e to the a. Okay, if we can write it in that form. Okay. If you have questions about that, you can ask me about that. You can ask the details. It's not that hard to show. I just don't want to spend the extra 10 minutes to do it. Okay. So what that tells me is then this thing here, which is equal to that, which is equal to that, which is equal to that, which is equal to this, which when we take the limit as n approaches infinity, I've now written this as an a to the n over n, right? 1 plus a to the n over n to the power of n. And these things are converging to t squared over 2 as n goes to infinity. And so this limit here is going to converge to e to the t squared over 2. And we're done, right? Because this is the moment generating function for z, right? My standard normal random variable, which is exactly what we wanted to show. It's one of those things where, notice, I put no structure on my moment generating function other than I could write a Taylor expansion for it, that it had a finite mean, or actually the mean was 0 in this case, but that was only to ease the calculations. If it's not 0, we just subtract off the mean, and now we have a random variable whose mean is 0. But the mean was finite, and the variance is finite, right? Which means that I could write out the first couple of terms, first few terms of this moment generating function. And under that assumption, and then I could write out a Taylor expansion for it, I've made a statement that every time we sum these things, or sum a standardized version of these things, I will always get the standard normal random variable. Great result, right? Every single time that limit is going to be the same thing. Give yourself some different ones and try it out, and you'll see the moment generating function does approach it in conversion. So where does this normal random variable come from? It comes from everywhere, right? It comes from everywhere as long as I start summing enough independent and identically distributed random variables, I will get it. So that is our proof. We've done this once and for all. I'll just say there are other ways to prove this. There are ways to prove this using differential equations. There's a few different proofs to this. There's some slight different variations as to how we set up our assumptions, but we're happy with it right now. We have the result. Now I want to spend, what has it been, 30 minutes? I want to spend a little bit of time going through two examples of how we use it. So I'm actually going to pause my video for a moment, and I'm going to reset the board, and we're going to answer a couple of questions using the central limit theorem. All right, so here's an example of central limit theorem, or how we might use the central limit theorem. Okay. So here's my experiment. I'm going to take 1,000 six-sided dice, and I'm just going to roll them all. 1,000 fair six-sided dice, and I'm going to roll them all. Right? And I actually have two different problems I'm going to set up. Right? One is I'm going to take the sum of the results of the individual dice. I'm going to look at the sum of the results of the individual dice. And then the other one, I'm going to take, I'm going to let y equal the number of sixes rolled when I roll 1,000 fair six-sided dice. Okay. So let's take care of A first. Let's look at that. Okay. So S is the sum of all the rolls. Let's let x of I be the result of, let's just say, dice I. Okay. Right? Because then my S is just equal to the sum of those x of i's. So there's a couple of things. Let's see. So the expected value of x of I, this is an old question now at this point, right? This is chapter 2, expected values. It is the outcomes times the probability of those outcomes. I'll let you go back through, and I'm sure we did it for this one at some point. The expected value will be actually 21/6, right, is 3.5, is what our expected value is. And our variance, well, our second moment of one of those x of i's will be 91/6, right? I can come up with a table of 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6, right? So on and so forth. So I can get the second moment, and the second moment is 91/6. Okay, and so then the variance of x of I of one of those is going to be, and I calculated these ahead of time, 2.9167. Is that right? So this minus this squared, 2.917, looks good for variance. Okay. Standard deviation is what I'm really going to have to figure out, but there you go. Okay. So what I have is I have these independent, because there's dice rolls and the dice are not dependent on each other, and identically distributed. Each dice is going to give me the exact same results, or at least the exact same probability mass function. And the expected value of one dice is 3.5. The variance will be 2.9167 approximately. That we really rounded that one there. And so when I look at the sum of those results, I equals 1 to 100, I can figure out the expected value of the sum, right, will just be n times, in this case, 1,000 times 3.5, which is 3,500. 3,500. Okay, and I can figure out the variance of S. It'll be 1,000 times the variance of one of the rolls, which is 2.9167, okay, which would be 2,916.7 or something along those lines. Okay, which now is equal to 54.006 squared. Okay. Give me a second. So, there's our variance for S. Okay? So here's how we use the central limit theorem. So let's ask this question. I see everything centered around 3,500. Let's ask the question, what is the probability that when I roll these 1,000 dice, I get a sum between 3,400 and 3,600? Now, if I had to compute this from scratch, this is a tough question, right? Because I have these 1,000 different dice that each have different types of rolls. I have this multinomial distribution, I suppose, where I'm summing the results, and that's not necessarily going to be an easy thing. Except for now I realize, oh, I'm just summing independent, right? I'm just summing independent random variables, and I know the mean and I know the standard deviation, so that this probability would be approximately equal to the probability I would get when I take my, I'll write it in the middle, S, and I subtract off my mean, and I divide by my mean, which is my 3,500, and I divide by its standard deviation, which is 50.006. That this is going to be approximately standard normal. So on this side it'd be 3,400 minus 3,500 divided by 54.06, and on this side it would be 3,600 minus 3,400 divided by 54.006. And that this is approximately standard normal. Okay. So what I would get, let's see, this number here is, what are my numbers on this one? Negative 1.852 and positive 1.852, which just says this should be the probability, should be the cumulative distribution function for the standard normal random variable if I plug in a 1.852 minus the cumulative distribution function from the standard normal random variable if I plug in a negative 1.852. And now I go back to my table of values. I start looking up these things off of that table of values, and I notice I get something like 0.96796 minus 0.03204, which is 0.39359 or something in that. So I take this result that involves many random variables that I'm summing together. And the central limit theorem says in that limit, the sum should be approximately normally distributed. So when I normalize that sum, it should be approximately standard normal. So I'll do that on either side. I'll plug those values into my standard normal random variable, which is look values up off the table, or use R over there, which we'll use in a second, and I can figure out that probability. And I see 93, almost 94% of the time, I expect that sum to be somewhere between 3,400 and 3,600. Okay? Even though I'm rolling so many dice, and there could be so many different results, that, again, only 6% of the time, approximately, a little more than 6% of the time, do I fit outside of that range. So if I roll those dice and end up with 3,300, a sum of 3,300, I'd have to start questioning whether or not those results, those dice are actually fair dice. Right? Because that's not something that would normally happen. If I roll those things and I get 4,000 as a sum, I mean, we can compute the probability that it's at least 4,000, but that's something that would never happen. Right? We can see how clustered these results end up around the mean, that they're actually, even though the mean is equal to 3,500, they're going to end up within a very likely, most of the probability is going to end up between 3,400 and 3,600. So there's an example in the central limit theorem where I can just take my sum and I can normalize it, and I can use my standard normal table. Now notice here I have the same thing. If I wanted to think about it this way, I could let y sub I equal a 1 if dice I, there's a 6 on dice I, right, and a 0 otherwise, right? And then my y is just the sum of these y. Right? I would also recognize that as a binomial random variable, which is the sum of these independent Bernoulli trials. So again, same situation. Right? So let me just think about this as a binomial random variable. My y is actually binomial with mean equal, how many 6s do I expect on this? Well, NP, right? It's binomial where n is equal to 1,000, and p, the probability of success of rolling a 6 is 1/6. Okay. So my mean is NP is 1,000 over 6, about 166.667-ish, right? 6 repeated actually. And my sigma squared, my variance, will be NP1 minus P. So it'll be this times 1 minus P, which would be 5/6, which would be 5,000 over 36, which is approximately equal to 138.8889, which is approximately equal to 11.785 squared. I'll just write my variance as some number squared. Okay. Okay. So again, I can just figure out the mean of this sum of random variables, in this case a binomial random variable. I can figure out what its variance is going to be in a case like this. And then the question, what is the probability? So here I'm going to roll these 1,000 spare 6-sided dice. And I want to know what's the probability that I roll fewer than, how about 150 6s? Roll fewer than 150 6s. And I know if I normalize this, y minus its mean, which is 166.67, divided by the standard deviation, which is 11.785, 150 minus 166.67 divided by 11.785, that this is approximately a standard normal random variable. Okay. So when I go ahead and figure out that this number right here is negative 1.4145, or thereabouts, then this probability is approximately equal to what I get when I plug negative 1.4145 into my standard normal random variable. So I'll look it up off my table, and I'll get 0.0786. So I roll 1,000 dice. What is the probability? I expect to get 166 2/3, right, or almost 167 6s. What's the probability I get as few as 150 of them? Well, it'll only happen about 8% of the time, 7.86% of the time. Okay. So let me finish this up here. Let me finish this up with R. Let me just point out, let's see, I'm going to switch over to R here. Okay. That if here you don't need to see my back. Right. So if I'm looking at R, notice what I have here. So I am going to use this sample function. A sample function is what I can use to pull from a distribution. So I'm going to take the numbers 1 through 6, equally likely. I'm going to sample from that 1,000 times with replacement, meaning I'm allowed to take the same number more than once. And if I do that, for instance, oops, try that again. If I do that, here's the results. Okay. I could take the sum of that, right? And notice this time I did it, I got 1,000, 3,510, 3,564, 3,500, right? Wow, it's always above 3,500, right? There's 3,430. Notice what I'm getting, and I'm getting a lot of numbers sort of in the range I would have expected to. And then there's another function called count. And count will just tell me the frequency of everything that occurred. So if I were to do this, notice I had 175 6s that time, 169, 156, 172, 160, so on and so forth. So if I just want to count, I just want that 160, I'm going to use, I'm going to refer to the 6th row and 2nd column of that data frame that's right there. Okay. So here's what I'm going to do. I'm going to set up my random variable. I'm going to do both of these experiments, A and B, at the same time. Okay. And so I'm going to, actually I'll put myself up in the little corner there. There you go. You can see what's on the board at the same time potentially. I'm gonna run this experiment 10,000 times, where I've rolled the dice 10,000 times, and I keep track. I roll the dice 10,000 times. I keep track of the sum of the dice. I keep track of the number of sixes of the dice, and it doesn't take long. It probably took about 3 to 5 seconds to do that. And now let's look at a histogram for S. The claim is that should be a standard normal, or it should be approximately a normal random variable. But this question of what's the probability that I get something between 3,400 and 3,600, I'm gonna compute the number of occurrences, or the likelihood of the occurrence in each of those cases, subtract them, and notice, what did I get? I get a 93.48% or a 0.9348 probability. Okay. So here's my normal random variable fitting inside of there, and I see the mean. And what was I expecting to get in that case? 93.59. Okay, so 93.48 is not a bad approximation for 93.59. Okay. So the other case, let's see, Y. Let's look at a histogram for Y. So that's, if I perform this experiment 10,000 times, the number of times I get, the number of sixes I get in each of those experiments. And notice it seems to range on the lower end from about 130 to the upper range, looks like over 110 or so, or sorry, 210. So now I want to know, well, how many of those occurrences were less than 150? And it looks like 0.0742. And it was supposed to be 0.0786, which does not look like a bad approximation. The actual central, 86, oh yeah, which is what I had there. Yeah, so there's the exact answer. And notice the normal, if you look at it carefully, the normal distribution doesn't quite fit it as well. But my original random variable started out a little more skewed than it did in the first time. Okay. It fits it pretty well, but notice things are skewed a little bit to the left. The values on the left are a little bit higher for my actual random variable as opposed to the normal, and the things on the right are normal. It's almost like the normal random variable was, you're blowing at it from the right-hand side, and it's sort of tilting a little bit. It's moved the probability. That's what's called skewness, by the way. Okay. And so I would expect this to give me a little worse of a probability of an estimation, but it still looks pretty darn good. Okay. So just following up, right? It didn't matter. Those were two very different random variables, or two different random variables, and even so, even though we had these two different random variables, we were able to use the central limit theorem to compute those probabilities, to estimate those probabilities, and we were able to do so with a very good estimation. Okay. I probably will follow up with a 30-minute lesson in which we talk about a couple of other additional estimations of the central limit theorem. We'll see how it all works out, but that said, incredibly powerful tool, makes our standard normal random variable even more valuable than it was before. Right. Have a good day.